Hi, my name is Jim Watkins, and I'm going to provide an update on lower food web monitoring of Lake Ontario. I'd like to acknowledge my co-authors, Lars Rudstam, Kristen Holick, and Steph Fagari of Cornell University, as well as Alexander Karateyev and Luba Berlikova from SUNY Buffalo State. So there has been concern that a decline in nutrient levels had led to lower fish biomass. And this relationship can be modified through lower food web relationships. Zooplankton are food for forage fish and for early life stages of fish. And the relationship of nutrients and fish can be modified by things like invasive species, for example, quagga mussels, as well as ones in the plankton, including Cercopagus and Benthic, the fishhook and spiny water fleas. There is a wide range of vertical distribution behavior exhibited by zooplankton and mysids, which overlaps with different fish species. And fish predation does modify plankton and mussel size distribution. Lower food web monitoring of Lake Ontario includes a New York State biomonitoring program led by several regions of New York DEC, U.S. Fish and Wildlife Service, USGS, and Cornell. This includes both nearshore and offshore sampling reported annually. It's a long-term time series back to 1995. It's typically biweekly nearshore and monthly offshore, and it is paired with water quality measurements. Cornell is also involved in the US EPA Great Lakes Program Office sampling of all 5 Great Lakes, including Lake Ontario. This is primarily an offshore focus. It is a long-term time series, but it is limited in seasonality, whereas we sample April and August. We also collaborate with DFO Canada, including Warren Curry and Kelly Bowen. They also have long-term lake-wide monitoring programs, and we closely coordinate sampling and analysis methods and often compare data. So the New York State biomonitoring program has the nearshore sites I described as well as offshore sites, whereas the EPA routine sites are primarily offshore at 8 sites. So in this presentation, I'll start with Benthos, which is the continued expansion of quagga mussels in Lake Ontario. Also turned to mysis shrimp, and good news with sustained population levels relative to other Great Lakes. Turning to zooplankton, the biomass has been stable long term, particularly relative to Lake Huron, which had a crash in 2004. Yet we do see a community shift towards calanoid copepods, which is generally an oligotrophic indicator. Our PhD student, Stephanie Fagari, is currently looking at the BMP versus the EPA data and is finding that the nearshore data may represent an early indicator of change that happens later in the offshore. And I'll wrap this up by also showing some trends for predatory cladocerans. Starting with Benthos, in 2018, there's an extensive Benthic Survey done by the Buffalo State Group, including traditional ponar grabs, as well as a new thing called the Benthic imaging system, shown here, which produces high-quality video imagery of the substrate, and also including gobies. So the results have been published recently in 2 articles, one looking at Dreisseniid expansion over the last 30 years by Sasha, and also Luba looked at the past 60 years in Lake Ontario, looking at the changes in benthic communities using these lake-wide surveys done over that time. Now, both of these articles are part of the Journal Great Lakes special issue coming out in April 2022, called Stressors and Successes, Lake Ontario CSMI Intensive Year 2018. And there are 16 published articles, including ones on bloater, cisco, lake trout, and Atlantic salmon. So this shows density and biomass of quagga mussels at different depth intervals and then a whole lake estimate. For density, we see that over time, density has seemed to level off. However, biomass does continue to increase, and that's due to the same mussels becoming larger in size. So we do see continued increase, and it is a very large mass of mussels, which is considerably more than both Lake Michigan and Lake Huron. Now, this can have some pretty big ramifications with clearance rates of the lake, as well as nutrient dynamics. There's some concern that they're acting as a large phosphorus sink, which may be causing an imbalance between nutrient loading and offshore concentration. Turning to mystids, we have kept a close eye on them during the intensive years of 2013 and 18, where we do seasonal sampling and keep track of cohort dynamics. We see consistent growth and reproduction, which is good news. When we look at time series relative to other lakes, Lake Ontario is the pink line in this graph. And the arrows point out the two intensive efforts of 2013 and 18. You can see a stable density of mysids. Whereas blue with Lake Michigan has seen a recent decline, which is approaching the green of Lake Huron. It's a very low numbers in recent years. Now, Toby, our grad student, has looked at maybe a relationship of mysid density to surface chlorophyll. And since Ontario is slightly higher in surface chlorophyll than the other lakes, it is intriguing that perhaps mysid density is, as supported by surface chlorophyll concentrations. Whereas in Lake Michigan, where surface chlorophyll has started to decline, we see a decline in density. So the zooplankton in Lake Ontario include several copepods, which include the calnoids, which are in blue. We have the dark blue is Limnocalanus macruris, a particularly large deepwater species. Light blue are other calnoids. We also have the cyclopoid copepods, which are in yellow, which is particularly characteristic of Lake Ontario, Dicyclops thomasii. We also have cladocerans, which act as grazers. So we have daphnids in red, and then smaller bosminids in green. And looking at the long-term time series in the nearshore, we see a pretty sharp decline in biomass in the late 1990s. But then pretty stable since then. There have been increasing amounts of calnoids in the nearshore over time. And again, that's potentially an indicator of oligotrophication. Now on the offshore, we've been able to compare to other Great Lakes, and Lake Huron was a particular example. In 2004, it saw a pretty sharp decline of offshore zooplankton biomass. Notice that that was mostly due to the loss in the important grazer cladocerans. Lake Ontario had a similar change in community in 2004 with a less cladocerans and cyclopoids, but sustained biomass. So increased amount of calnoids and Limnocalanus seem to replace those. We were able to collect the last 2 years of data, even though of COVID. We had a lot of help from the Canadians, and USGS. And so we're able to continue that time series, and it seems pretty similar trends since 2019. Now, Steph has been able to compare the biomonitoring and EPA programs offshore and find that they generally agree. This is paired estimates of each of these, July for biomonitoring and August for EPA for the past decade. And you can see the species composition does appear, and the biomass appear very comparable. Now turning to exotic predatory cladocerans, which includes the Cercopagus or fish water flea and the Benthic spiny water flea. Cercopagus is an angler nuisance where it fouls fishing lines and causes problems with that, whereas Benthic is a much larger species and has been identified as an important fish prey item by Gatch et al. 2021 for Cisco diets. We see that they have different seasonal dynamics, where Cercopagus tends to peak earlier in June versus the Benthic is later in September. Now, for a long time, even though Benthic was introduced in 1985, it really didn't appear that well. This is the solid black line. You can see that there was a resurgence after 2004, both in the nearshore and the offshore. And there's some thought that that may be due to lower alewife abundance, a lack of predation pressure on this larger species. I wanted to note that these zooplankton community shifts do mirror a shift in vertical distribution. So I show a schematic of a 1990 zooplankton community where we see shallow species of cladocerans, Daphnia retrocurva, as well as more cyclopoid copepods, which are generally in the Metalimnion, and a few deep water calanoids. Whereas shifting to 2020, we see a shift to more deep water Daphnia, the Daphnia mendota, less cyclopoids, and more deep water calanoids. And note that this is generally a shift toward larger individuals, which is also an indicator of lower fish predation pressure. So I'd like to wrap this up by just putting it out there that we are interested in supplying lower food web data needs for fisheries in the intensive year 2023. So this could be identifying selectivity through diet and plankton analysis comparisons. We see a need for improved coordination with the timing and locations of larval fish emergence, which particularly spring and nearshore samples. We do see continued benthos and mussel monitoring happening in 2023 at a similar scale. And then we do see a need for collecting food web components for stable isotopes and fatty acids, as well as looking closer at size distributions. So my email is jmw237@cornell.edu. Happy to take any questions, and thank you for listening.